Good afternoon, students. Good afternoon. Let's go, guys. Let's go. We have spent some time last time looking at heat capacity, right? And good. So to bring us back up to speed, we're going to just quickly review or just quickly recap, essentially, what we would have covered last time in terms of heat capacity. So we would have said that when we talk about the heat capacity of a substance, heat capacity of a substance is just the amount of heat energy that is required to cause a change in the temperature, right, by 1 degree Celsius or 1 Kelvin, right? 1 degree Celsius or 1 Kelvin. Now, in other words, we could say it's the amount of heat energy required to cause unit change in the temperature, right? So to change the temperature by a factor of 1. So if it was at a certain value, how much heat energy is needed for it to go up by 1 degree Celsius or 1 Kelvin. Now, we would have went through and we would have also looked at an example, right? And I would have also stated that when we're doing the calculation, because if you can remember, we would have written a formula where we use that formula to actually calculate or actually relate the heat energy to the heat capacity of the substance, right? And we would have seen that the formula would have included that the heat energy is equal to what? C, which is the heat capacity multiplied by the change in temperature. So that's the formula, right? We said that the heat energy, it is equal to the heat capacity of the substance multiplied by its change in temperature, right? And a good way to remember that equation is if you think of cat, right? Because if you can remember the formula, yeah, most of them done. I think this one is working. So if we say, for instance, EH, which is the heat energy, is equal to big C times the change in temperature. So if you look at it from the correct angle, right, it will look like cat. Yes? Yes, sir. Right? Okay, but that's what I'm saying. If you look at it at the correct angle, right, you will see cat. Can I see cat? But if you imagine, right, at least if you imagine, you could say the triangle is like an A. Right, so it's cat. So we can remember it by just cat, right? The heat energy is equal to cat, where C is the heat capacity. Now, in terms of the change in temperature, we would have done an example where I would have expressed the change in temperature in degrees Celsius, students, in degrees Celsius, and I would have said that the change in temperature in degrees Celsius is the same in Kelvin. So we're going to look at an example and we're going to just talk about that first before we go into what we're going to be talking about today. So let me just head up. So we're going to continue with the concept of heat capacity. Heat capacity. All right, so heat capacity. All right, so we're going to look at an example. So let's say that we have a block of metal, all right, let's say it's at room temperature, which we're going to say about 25 degrees Celsius. At 25 degrees Celsius is heated, is heated by, I'm going to say by a torch, to, let's say to about 150 degrees Celsius, example, right? To 150 degrees Celsius. And we're going to say that the heat capacity of the metal, or let's say of the block of metal, is, let's say, we're going to say probably about 240, right? 240. And the unit we use for heat capacity is what again? Joule per Kelvin, right? And when we hear these units, we should have an idea as to what they're really telling us. No, you don't have an idea? So we say 240 joule per Kelvin. So what we're saying is that the metal in question, it requires 240 joules of thermal energy in order for us to see a change in 1 Kelvin. So every Kelvin requires, or every change in Kelvin requires 240 joules of energy to cause that change. Okay? So that's what we see with that. So we have this example right here. We're going to just work through, and I'm going to get an opportunity to take some time to showcase why it is that we say that the change in temperature in Celsius is going to be the same in Kelvin. So we're going to look at that. Yes. 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 You're going to have a lab. Yes. Next week. Yes. Next week. All right? But there's something we have to look at, which is we're going to talk about it today before we do the lab. Yeah, related to it. All right. So, example. So, in this case now, we can remember the EH is equal to what? Cat? Yes. EH is equal to cat. C delta T. The heat energy, EH, is equal to C delta T. Okay? C delta T, where C is the heat capacity and delta T is the change in temperature. So, we're given that C is equal to 240 joule per Kelvin. Now, we need to find the change in temperature. Now, we know that the change in temperature, delta T, is just the final temperature minus the initial temperature. So in other words, just the difference in temperature. Now, oftentimes, we can come across scenarios, where we might have T2 being less than T1, right? But again, just remember that we're finding a change in temperature, right? So all you're doing essentially is just subtracting the smaller from the larger, right? So we're just subtracting the smaller from the larger, because in some scenarios, because in this case, we're looking at a scenario where we have the object at some temperature and we supply heat energy. So in that case now, we're going to see that there's going to be an increase in temperature. So when we look at supply and removal of energy, we usually associate any supply in energy to cause an increase in the energy of the substance. So we're going to get a positive value when we find the energy. But if we're removing heat now, we're going to associate that to a reduction in the amount of energy. So it's going to be minus. Right? So if you're adding heat, it is positive. But if you're removing heat, it's going to be negative. When adding the temperature must go up. Right? Or if you work it out and get a positive value, then you're adding heat. But again, as I said, just to make the calculation more meaningful in the context of what we're discussing right here, we ignore or we don't pay attention to whether or not we're adding heat or we're supplying heat in terms of the sign. Right? So at all times, we're going to aim to get the heat energy being a positive value, because again, we're just going to be subtracting whichever is smaller, the smaller temperature, from the larger temperature. Right? Because again, we just want to know the change in temperature. Okay? So again, students, all we're finding with delta T is just a change in temperature. So just always remember to subtract the smaller from the larger. Again, just always remember to just take away the smaller from the larger when you're finding the change in temperature. That's all we have to do. Okay? In our case, right? So remember, in our case, just subtract the smaller from the larger, because when you look at, because you're going to cover this also in chemistry. And in some cases, we might want to know if it's endothermic or exothermic, right? And if it's endothermic, it's losing heat. So the heat energy is going to be negative. So again, as I said, in our cases, we just subtract the smaller from the larger, because we're not responsible if it's endothermic or exothermic, all right? Anyways, so we're right here now. Now, let's find delta T right here. So to find delta T, we will simply just say, okay, T2 is 150 degrees Celsius and T1 is 25 degrees Celsius, which equals now, yes, you can go, which is 125 degrees Celsius. Now, I would have stated that once we're talking about a change in temperature in Celsius is the same change in temperature in Kelvin. So what we see then now is that if we have a change in temperature of 125 degrees Celsius, that's going to be the same as what? 125 Kelvin, right? But, so a change in temperature in Celsius is the same change in temperature in Kelvin. Okay? Only students, only when we talk about a change in temperature, we see that, okay, it's going to be the same in Celsius as in Kelvin. Okay? Now, notice that in our formula, we have C is the heat capacity in joule per Kelvin. So, we would want to have the temperature to be expressed in Kelvin. So we can just simply just state the difference and just write this as 125 Kelvin. Now, if you want to see why that is the case, why we can write this as just 125 Kelvin, even though we know that, okay, if we're converting from Celsius to Kelvin, we add 273. In this case, because we're talking about a change in temperature, they are the same. So I'm going to show you, right? So let's do it. So let's say change in temperature, delta T, is T2 minus T1. Now T2, let's do that now. So we're going to express T2 in Kelvin. So we're going to say T2, yes, 150 plus 273 minus 25 plus 273. All right? This now would have give us what? 423 minus 298. And again, this is Kelvin minus 298 Kelvin. When you subtract that, what do you get? 125, right? So we see that it works out. So to prevent you from doing all of this, just remember that, okay, once you take the difference in Celsius, it's going to be the same in Kelvin. Okay? Yes. Plus 273, yes. Every time. That's the constant. Yes, you're going to get this on your test. So remember, students, just take the difference in Celsius and just write it as Kelvin because it's going to be the same thing. So you don't have to do this. Right? Don't have to do that. So now we can plug these in now. So we can say that C is 240 joule per Kelvin. And delta T now is 125. Right? So 125 Kelvin. So now, what's this? Right? So 30000. And because we have Warburton, because we have Kelvin right here, and Kelvin, they cancel off, right? So we just get joule, which is energy, right? So that's what it takes to complete a question like this. So again, remember, subtract the temperatures, smaller from the larger, right? And whatever you get is going to be the same in Kelvin if it is that you're given in degrees Celsius. So when we talk about converting to Kelvin, that's only strictly when you're doing what? The topic before, the gas laws, right? That's the only time that you're going to be required to convert by adding the 273. Because again, we're talking about a change in temperature, then we can determine the difference in temperature in Celsius and express that as Kelvin by just saying, okay, they're going to be the same. Okay? Good? So that's that. So you guys can take that down and then we're going to move into a brand new topic. I mean, yes, in that context, but waves in physics is everything. Everything is waves. Because, right, you can talk about heat wave, you know, when you see it because of waves. As I'm speaking with you, it's waves. Sound. Right. Right? Yes. Everything is wave. Right? Huh? Yes. Yes. Huh? Yes. Right. Okay. All right. Because the thing is, you see, all right. You see what we might think of as waves, right? Like you got a beach and you see the waves. A wave. Listen up. Listen, students. A wave is just a means of transferring energy. That's what a wave is, right? So when you're at sea or the beach or whatever, and the wave lifts the boat, that's because energy is being transferred in that scenario, right? So when you're listening music and you feel the music come to your bones, the waves, right? Right? Right. You're not supposed to be taking those buses. Yeah? You're supposed to be taking those buses. Yes. Yeah, let's do it now. We're going to do it. No. When we start waves. And we'll make the telephone. Yes. Yes, so we're going to do it. Yeah, it does work. Yeah, it's physics. It must work. It must work. All right? All right. Anyways, let's go back to the thing now. So, all right, so let's go now. Let's go. So, we're still on the idea of heat capacity, but we're going to be a little more specific. Right? So again, students, we're still on the idea of heat capacity, but we're going to be a little more specific. So therefore, what's our topic? No. So we're still on the topic of heat capacity, but we're being a little more specific. Heat specific? So again, we're still on the topic of heat capacity, but we're being a little more specific. No? It starts with specific. What? Capacity, specific heat capacity. Right? So again, we're still talking about heat capacity, but we're being a little more specific. Right? So, specific heat capacity. That's our topic now. Specific heat capacity. Now, just like with heat capacity, we can represent this quantity by a symbol. And for that, we use a C as well, because it makes sense. Right? We use C, but because we had reserved the uppercase C for heat capacity, then we have to use a lowercase one, right? So that's specific heat capacity. Now, we would have said that the heat capacity is the amount of heat energy required to raise the temperature of whatever amount of that substance by 1 degree, right? 1 degree Celsius or 1 Kelvin. Now in this case now, because we're talking about specific heat capacity, we are going to be interested in a specific mass, right? A specific mass of the substance. So for the specific heat capacity, we say that this is the heat energy required to raise the temperature. And again, we have to be specific in terms of what mass of the substance. So we say to raise the temperature of 1 kilogram, right? 1 kilogram of a substance by how much? No, man. By 1, right? By 1 degree. Right? So in other words, 1 degree Celsius or 1 Kelvin. Right? So that's specific heat capacity. It's the amount of heat energy required to raise the temperature of specifically 1 kilogram of that substance by 1 degree or by unit temperature. So 1 degree Celsius or 1 Kelvin. Okay? With the specific heat capacity now, what we see now is that if we have an object, let's say for instance we have a piece of metal, right? If we have a piece of metal like this, what we're going to see is that no matter how large the metal is, it's going to have the same specific heat capacity. So if we have this block of, let's say this is aluminum, and we have a larger one, it's going to still have the same specific heat capacity. Because again, the specific heat capacity is exactly how much energy is required to raise 1 kilogram of that substance by 1 degree. So if we want to calculate the specific heat capacity, we'd have to cut off 1 kilogram, right? And then apply heat energy and keep track of how much heat energy is being applied, and then see when it causes a change in temperature. So what we're saying, bottom line is that when we talk about the specific heat capacity, we can use that to identify the type of object. Okay? Because if you have a piece of aluminum, it's going to have a certain value for its specific heat capacity. So no matter how large it is, it's going to have that same specific heat capacity. However, we're going to see that if it's this piece of aluminum compared to a larger one, we're going to expect the larger one to require more heat energy because of its larger mass. Right? So just wanted to allow you to be aware of that scenario. So again, we can use the specific heat capacity to identify an object. And our experiment is going to require us to identify an object by considering the specific heat capacity. Okay? Miller? Good? All right? So that's that. So now, let's look at the equation. Right? Let's look at the equation. So to calculate or to relate the heat energy to the specific heat capacity of the substance, we can write that heat energy is equal to, in this case now we're going to have M. What does M represent? Mass, right? And we're going to have C, and then we'll write back this term, delta T. Right? MCAT. Good. Right? So EH, which is the heat energy, is equal to MC times the change in temperature. Now, we're going to talk about the terms and their respective units. So EH is the heat energy. And for most cases, we'll talk about heat energy that we supply, but we could also agree or accept that we could also be removing heat energy. Because if we remove heat energy, it's going to cause a change in temperature, but it's going to cause it to reduce. Right? So EH is the heat energy that could be supplied or removed, and this is always measured in what unit? Joule. No man, energy. Joule, right? Joule. Right? Now M is the mass, and mass is in kilogram. Right? And C now is the specific heat capacity, and this is measured in what? What will this be measured in? J slash K. J slash kg, close. So if we make C the subject, right? If we make C the subject, we're going to get C is equal to EH over M delta T. So EH is measured in joule, so we're going to have joule over mass is measured in kilogram, right? And the change in temperature is measured in Kelvin, right? So this is the same thing as joule per kilogram per Kelvin, right? I was just testing you guys, right? I can't underestimate my students. Right here, in joule per kilogram per Kelvin. One more. All right? And then delta T now is the change in temperature, right? And this is measured in Kelvin. So that's what we see, right? So again, note that the specific heat capacity is measured in joule per kilogram per Kelvin, right? So joule per kilogram per Kelvin. So it's how much heat energy is required to change the temperature of 1 kilogram of the substance by 1 Kelvin. So that's what we see right there. Now, we're going to show a relationship. So we're now going to show an expression that relates the specific heat capacity to the heat capacity. So let me go over this side. So we're going to say that the heat capacity, no, it's a formula I'm going to share with you, of a substance is related to its specific heat capacity by the expression, right? So by the expression where we say that the big C is equal to, right, little c, but m times little c, right? So C is equal to mc. Yes. So this formula right here relates the heat capacity of a substance to its specific heat capacity. So we get C is equal to m times c, where C right here is for heat capacity, and then this C right here is for your specific heat capacity. So that's one other expression that we need to be comfortable with, because it can be asked, no, not rip it off. It can be asked by anybody that we see on the road, what is the formula that relates the heat capacity to the specific heat capacity? And you will have to tell them, right? You will never know. Right? You will never know. You know, you will never know. So you have to be prepared, right? Just in case, right? Just in case. So we have that right there. So we're going to look at one example, and then we're going to flow into talk about how we can find the heat capacity of a substance experimentally. Okay. This joule per Kelvin, right? Because this would be joule per Kelvin. All right, let's do this side first. This would be kilogram, right? This would be joule per kilogram per Kelvin. So the kilograms will cancel off, right? Leaving it with joule per Kelvin. Okay? So it works out. So we're going to look at maybe 2 examples, right? And then we're going to talk about how we can actually work on the experimentally determine the values for the specific heat capacity of a substance using one of 2 methods. All right, so example. All right, so example. So, and you know, before we look at some examples, really, I should share some values with you, ladies right here. I should share some values with you. Not necessarily some values, but one value that you know you will actually see quite often. And I guess in the example, I will highlight it in the example. All right? So let's say example right here. So we're going to say, let's say so let's say that a beaker containing, so a beaker containing let's say 25 or 250 grams of water at probably, Daniel, what's the temperature of the water? 30. 30 degrees Celsius, right, is heated to, let's say it's heated to 80 degrees Celsius by a Bunsen burner. A Bunsen burner. All right? Now we're going to say now calculate the heat absorbed by the water given its specific heat capacity. Specific heat capacity is this value. You're going to see it quite often, 4200 joule per kilogram per Kelvin. So this value right here, students, we're going to see it quite often, right? This one, yes. So this value right here is the specific heat capacity of water, right? So water, again, as I said, we can use the specific heat capacity to identify the substance. So if we get a substance and we're told that its specific heat capacity is 4,200 joule per kilogram per Kelvin, then we know that we're talking about water. Water. Water, 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 water. Right? So this is the specific heat capacity of the water. So now, to work this, we start with our formula. Right? So we say that the heat energy, Bunsen, right? So EH is equal to M what?
C, MCAT.
MCAT, yes? So we have EH, students, focus again. EH is equal to MC times the change in temperature. Now, we're giving students that the mass is 250 grams, right? C is given right here, and we're told that the temperature was at 30, then it go up to 80. So let's note down some variables right here. So we have the mass M, that's 250 grams. But notice over here that we said that we want to have the mass in kilograms. So we're going to have to convert this to kilogram by doing what? Dividing by 1,000. All right, so we divide by 1,000, which is 0.25 kg. Now C now is 42 per Kelvin. All right? Yes. All right? And then the change in temperature now, delta T. That now, we're going to have T2 minus T1, which is 80 degrees Celsius minus 30 degrees Celsius, which is what? What's that? 50, right? 50 degrees Celsius or 50 what? Kelvin, right? Because the same thing, because there's a change in temperature. So they will be the same thing. Plug in this now and work out. So M is 0.25 kilogram. Times 50 Kelvin. 52 much? Like that? Is that right? Yes? And this will be what now for the unit? What's the unit? Joule. Alright? Yes, good. Good work. Alright, so Warburton, what we're saying is that SHC is specific heat capacity. Okay? So that's how we work a question like that. So it's pretty straightforward in terms of these. Huh? Right? So that's what we get right there. Because the mass was 250 grams. Right, to convert it to kilogram. Okay? Yes. Yes, convert and yes, I would say convert, but again, there's a caveat to that. In the sense that, I mean, we can have situations where we can get away with not converting, but when those examples come about, we'll address them. Okay, but for now, convert. Right, we said that we're going to look at the different methods of determining the specific heat capacity. But before we do that, I'm going to look at one more example. One more example. So let's do that over here. So while you take that down, I'm going to erase this side. Probably look at maybe 2 examples so that we can reinforce this. All right, Nia? We'll look at probably about 2 examples so that we can reinforce this. So let's say students, we look at this example right here. So we're going to say that let's say 4 kilogram of water is heated from, let's say maybe 20 degrees Celsius by supplying let's say 8,000 or 8,500 joules of heat energy. All right? And we're going to say calculate the final temperature of the water. All right, so we're going to look at this example next. So just ensure that you copy down that over there and start taking this down so that once you start going through, you're able to follow along. All right, so that's where we are. All right, so we're going to look at this example right here. If you notice, we're asked to find the final temperature. All right, so we're going to see how we can do that. All right? Now, we should recognize, students, that in order for us to find the final temperature, we need to know what was the change in temperature. Right? So we're going to go into that right now. So let me just say this now. That will happen. That. Okay, so that's 4, that 16. Cool. Yes, we're going to do some transposing. Right. Right? Okay? All right, so let's go now. So let's go now with the solution. So we start out with the formula again. EH is MC delta T. All right? We are given that M is 4 kilogram. C is always 4,200 joule per kilogram per Kelvin. Once we're talking about water, so the specific heat capacity of water is always 4,200 joule per kilogram per Kelvin. Now, we can remember that delta T is equal to T2 minus T1. Right? We have T1 because we're given that it was at this and it was heated to some final temperature that we don't know. So we cannot do anything with this as yet. So let's first transpose so that we can find the change in temperature. Because if we know the change in temperature, we can rearrange this equation right here so that we can find T2. Right? So let's do that then. So we're going to find delta T. So all we do, divide this one, Sandy, by MC, and divide this one by MC. Right? So cancelling. So delta T is equal to EH over MC. Right? So what we do now is energy is this value, right? Can I add a 0 to this right here? Yes. Yes. Who confused? Yes. It's the same thing, same process. It's just that I'm just worried that we're going to get a small value right here for the temperature, that it's not going to be meaningful. That's for water. Water is always this. So in this case, we're talking about water. So we always use this as the specific heat capacity. Okay? Warburton? Joule per kilogram per Kelvin. It's always for water. Okay? Yeah, for water. So this now becomes, this number right here, 85,000. This is joule divided by the mass, which is 4 kilogram, times 4,200. And this is joule per kilogram per Kelvin. So, what do we get for this? 5.06? Okay. So that's what I was worried about. Or let's say 5.1. Right? 5.1, or we could just round this to 5. Let's say we round it to 5. So we're going to say 5 Kelvin. Right? Or we could say 5 degrees Celsius. Because again, it's change in temperature. So 5 degrees Celsius. Right? So again, I was just worried about the small volley right here and the energy change. Huh? Yes. No, man. All right. Remember, this is what? What's this? Change in temperature. So the change in temperature was what? 5. So what it means is that this would have changed by 5. So it's going to go to what? 25. Right? So let's show it right here now. So delta T is that. So if we rearrange this now, we're going to get that T2 is going to be equal to delta T plus T1. Right, when we transpose this, we add T1 to both sides. Right, because of the minus right here. So this now becomes 5 degrees Celsius plus 20 degrees Celsius, which is, okay? So it goes from 20 to 25 when we apply this amount of heat energy. Okay? So again, the process remains the same, right? What's different in this case is that we have to do some transposing and then we evaluate accordingly, right? So we made T2 the subject. So we have, because we want to know final temperature. This is what we're looking for. And T2 is the final temperature. Okay? So again, the maths have to be on point, especially when it comes down to rearranging the expressions and working. So we saw this right here. Now, I'm trying as much as possible with the time to provide you with examples, because part of your Part of the suggestions and the comments, wait, I don't want to lose my train of thought. Part of the comments that CXE provides is that we need to give students enough examples or opportunities to apply the principles, especially when it comes down to using the math. So I'm trying to give you guys, as I said, enough examples around these concepts so that you can do your transposing, you can do your substitution, you can do your necessary evaluation. Right? So anyways, we have this. Let's look at one more example like this. So over here. So we're going to look at this now in terms of a different approach which we might see. So we're going to say now, Williams, that an electric kettle. No, I'm going to go through it here. Electric kettle, yes. Right? Rated students at 1800 watts is used to heat water. Let's say specifically it's a question, it's an example. How much water would I use? Example. Like the mass. Yes. You will be given the value for specific heat capacity. Okay? Huh? 6 kilograms? But I think about like an actual kettle. So probably about let's say heat, let's say probably 0.8 kilogram of water. Out of water, initially at, let's say it's some water, you take out your refrigerator. It's probably about 12 degrees Celsius. The kettle is 100% efficient and was operated for, let's say it's for enough more energy. So it's operated for, we could say about 2 minutes. Let's see, 2 minutes. All right, 2 minutes. All right, for 2 minutes, and then we're going to say calculate the change in temperature of the water, hence find T2, which is the final temperature of the water. So that's our question. So again, this same principle, however, we have some additional things to consider, right? So we started off with the basic one where we just plug in and get the answer. We look at this one, where we did some transposing. Now we're looking at this one now, where we're going to have to consider some other things in terms of helping us to work this question. So, efficiency. You're not going to really use it in terms of any calculation, but it's going to be applicable, right? It's going to be applicable. So let me just allow you to take that down and then we're going to go through. All right, so we have this thing right here, right? And the examiner says we need to calculate the change in temperature of the water and hence find the final temperature. That's what the examiner wants us to do. So, again, we start off with the fact that EH is equal to MC delta T. Now, free it. Yeah. I same thing, I just have to write it. So EH is equal to MC delta T. So that's what we have right there. Now, in this case, we are told that we use an electric kettle, right, to heat the water. So what would be supplying heat energy to the water? Daniel? No, man. The kettle. Yeah, the kettle, right? So the kettle, students, is what is supplying the heat energy. Now, we're told, students, that the kettle is rated at 1,800 watts, right? Now, we should remember that this value right here represents the power rating of the kettle, right? So the power rating of the kettle, so in other words, how much power it consumes, and then essentially how much power it will actually convert, basically. So anyways, the power rating is 1,800 watts. And we're saying that, okay, it was used to heat this amount of water that was initially at 12 degrees Celsius. And the kettle, students, was being operated, it was 100% efficient, right? And it was operated for 2 minutes. So, what we need to consider now is this expression right here. So the heat energy is equal to MC times the change in temperature. Now, we know M. M is 0.8 kilogram. We know C, because it's water, so it's going to be, right, joule per kilogram per Kelvin. Right? Do we know EH? Do we know the heat energy supplied? No, so this is temporarily unknown. Do we know delta T? No, we don't, so this is also unknown. Huh? We know T1, but we don't know delta T, yes. Right? Now, delta is a change. Now, even though, students, we're not given a value for the heat energy, pay attention. Even though we're not given a value for the heat energy, we can determine that, right? Because we're given the power right here, and we're given the time. Now, there's a way to relate energy, power, and time. There's a way to relate energy, power, and time. All right? So, what's the formula, students, that relates energy, power, and time? All right, so P equal E over T, energy over time. So if P is equal to energy over time, energy, energy is going to be equal to P times T, right? Power times time. Now, what we can do now is we can use this expression right here to find out how much heat energy was supplied by the kettle. And again, remember the kettle is 100% efficient. So it's going to deliver all of the energy to the water. That's what we're assuming to make the example a little more meaningful or more simpler in terms of how much things we have to consider. So in this case now, we have the power. The power is 1,800 right there. Watts. Or we could say 1,800 joules per second. Right? And the time now is, what's the time? 2 minutes. So we're just going to put 2 right there. Okay. Convert to seconds, right? So this is 120 seconds. So that's how much now? Okay. So 21600. 216? That's how much? Huh? 110. Alright? Only for energy that. Yeah, portion of energy. Right? No, we're not finished yet. Okay. So, we have that right there. That's the energy. Now we want to find out, okay, what was the change in temperature? No, see this capacity right here. This by MC. Right? So, alright, so I'm just thinking now because again, I think I want to change the just one simple thing. If I do this, sign inside. No man, if I do that, yeah. Right? Yeah. Okay? So watch again. So we change the mass to 8 kilogram because I'm just worried, the amount of energy right here and what change in temperature it's going to cause. Right? So we have that. Then now, we don't know T1. T1 is 12. Right? So we start with the expression again now. So we say EH is equal to MC delta T. So because we want to find the change in temperature first, we divide by MCS. Yeah, well, that's exactly what you said. MC, like that. So delta T then now is equal to EH over MC. So EH is this big number, joule, divided now by M, which is 8 kilogram, times 4,200 per Kelvin. All right? Six points? Okay, so could I work with that? Could I work with it? Just to kind of start fret. Yes, they do. So we get 6.4. So it turns out that I could have used the 0.8, but I was just kind of panicking, yeah. So this is degrees Celsius. So then now, the final temperature then now, T2, so therefore, T2 is going to be the initial temperature, which is 12 degrees Celsius plus 6.43 degrees Celsius, which is 18.43 degrees Celsius, or simply 18 degrees Celsius. All right? So if you're using this kettle for 2 minutes, you're not going to get enough water to make a tea. You have to go heat it some more. All right? So that's what we get. All right, so we're going to talk about a method for determining the specific heat capacity, which is going to be related to your experiment. All right, so we're going to look at how we can determine the specific heat capacity of a solid, right? A solid, right? So determining the specific heat capacity of a substance, Johnny, using, how do I say spell? Determining, using the method of all right, so come again, students. So, method of mixtures. So, going to sketch out a little diagram to illustrate the method of mixtures, and then we're going to talk about the steps. involved. All right, Johnson? So, let's say we have this right here. So we have so we have this right here. We have something like this. And we're going to have some water inside this container right here, or this thing. So this is a beaker, right? Now, we're looking at, let's say we're trying to find the specific heat capacity of, let's say a metal, like a piece of brass. So, we're going to have this. Let's say something like that. And we have this tied to a string. Something like that. Right? And we're going to be supplying some heat. Right? And let's say we have a container. Yes, please. So, all right, so what we have right here, so we have our diagram right here. So we're looking at the method of mixtures, right? Now, with the method of mixtures, we will always know we'll know the specific heat capacity of one of the substance that we're working with. So in this case, we're working with the brass, which is a metal that we probably want to find the specific heat capacity of. And we have some water, right? Some water inside this container right here. Now, what we'll do is we'll actually, after probably heating this for some time, up to a certain temperature, so I may also draw a thermometer here. So we have a thermometer right here. All right? So, we have our thermometer. So let me label these up for you so you can appreciate them when you look back. Thermometer. All right? So this is a calorimeter. A calorimeter. A calorimeter. Right? This right here is our tripod stand. Tripod stand. This right here is our beaker. Huh? I soon talk to you, young miss. All right? So, and then inside this here, we're going to have water. So we're going to have water inside those containers. All right, so this is our diagram that we can use as a means of determining the specific heat capacity of this metal using the method of mixtures. So let me give you the steps. And then we're going to look at a little expression. So Daniel, give me track of the time here. Tell me I have 5 minutes left. All right, so one, we place the metal in the beaker of boiling water for, let's say, for 5 minutes. All right, two, we're going to measure, yes? Huh? Measure the mass of water in the calorie three. We're going to also measure the initial temperature of the water. No. You're going to see that your lab is going to have something similar to this, but for the sake of the example, I'm just kind of summarizing the method somewhat. All right? Then we're going to transfer the metal from the boiling water to the calorie meter. All right, and then 5, we're going to say, let's say, record all results. All right? So that's a summarized version of the procedure involved. For the lab, it's going to be more detailed. All right? It's going to be more detailed, so we have enough time. So, in terms of the calculation involved now, we will see that, watch me students, just pause the writing for just 20 seconds. So, when we have the metal in the water, boiling water, for 5 minutes, we're going to assume that that is enough time for the temperature of the water and the temperature of the metal to be at E word. Same, but not an E word. No? Equilibrium. Right? Same thing as the same, but equilibrium. Okay? So, the temperature of the water and the temperature of the metal is going to be the same. Now, what we're going to do is we're going to transfer, as we said right here, transfer the metal from the hot water into this water item, which is going to be at room temperature. Right? So what we're going to see now is that there's going to be some heat energy being transferred from the metal to the water. So we can say that the heat, let's say, transferred by metal is equal to the heat gained by what? Heat gained by what? What is gained in the heat? What's in this? Water. Right? Water. So then, the heat transferred, or the heat energy associated with the metal losing heat energy, we can calculate that by using MC delta T. But in this case, we want to be specific to the fact that, okay, we're talking about the metal, so we can say M for the metal, M for the metal, M for the metal. That will be equal to MC delta T. Right? But in this case now, this will be for what? This is water. So we can say W, W, W. So then, we can transpose to make this the subject. So we get Cm is equal to M W C W delta T W, and we divide by M M C M. Somebody still don't understand? Okay. I'm going to make sure so I go over it before you go. Alright? So we have this right here. Alright? So, we're saying, students, that the heat energy, that will be loss quote unquote, because it's not really lost, it's really transferred. So the heat energy transferred by the metal, right, will be equal to whatever heat energy is gained by the metal, right? Now we know that we can calculate how much heat energy is supplied or removed using EH is equal to MC delta T. So we're taking that into consideration now for our substances. So for the metal, we say MC delta T. But we add a little m right here to indicate that we're talking about the metal. Right? And that's going to be equal to MC delta T, but for the water. So we add the W. Now, to find the expression for the specific heat capacity of the metal, we divide both sides by M delta T for the metal. Yes. Good. So we made an error. So this should be M delta T. My bad. So good thing you saw it on young miss. So we divide both sides by M delta T. Right? So when we do that now, we get that the specific heat capacity of the metal, C. Alright, so what we're saying again is that we relate the heat energy that is transferred by the metal to the heat energy gained by the water. Right? We equate them as we did right here. We get our expression MC delta T for the metal is equal to MC delta T for the water. But because we're interested in the specific heat capacity of the substance, the metal in this case, we have to make that the subject. So we divide both sides by M delta T right here. And we divide this one by M delta T, which allows us to get that the specific heat capacity of the metal is equal to MC delta T for the water divided by M delta T for the metal. So we're going to be required to use this for our lab. So tomorrow when we meet, we're going to look at some examples around this.